Recording in progress.
Okay, so welcome everybody. Good morning. So we're going to start the session of a TCM, of a master's thesis by Victor Tarasov, entitled Asymmetries in Mutual Intelligibility and Information-Theoretic Approach. And this is a thesis supervised by David Sanchez. So as you know, so the routine will be, you will have 30 minutes to make your presentation. Then we will stop the recording, and the committee, which is composed by, well, David, Luis, and myself, we will make as many questions as deemed necessary, and only the panel will be able to make questions. So without further ado, let's see if someone else wants to come. Without further ado, so the floor is yours. You have 30 minutes.
Okay. Well, hi, my name is Victor Tarasov, and I'm going to present my master thesis, Asymmetries in Mutual Intelligibility, an information-theoretic approach, supervised by David Sanchez. The objective of this work has been to measure the distance between different languages within the same linguistic family. For the three main Indo-European families, the Romance family, the Slavic family, and the Germanic family. Based on the idea of mutual intelligibility, we have measured by generating distribution functions of phonemes, we have measured the distance between languages, and we have shown that there exists this asymmetry in the distance between the languages. So first, I will make a brief comment about the key concepts of this work. Then I will talk about the methodology and the validation process, which have been a very important part of the work. Then I will talk about the generalities of these three families, and finally I will talk about the distances with this relative entropy measure. Okay, so let's start with introduction. Just a brief introduction. Intelligibility is the listener's ability to recognize and to understand the message in sequence, and it depends of different factors, such as linguistic factors. For example, the shared words between the speakers, also in extra-linguistic factors, such as the attitude towards the foreign language, and paralinguistic factors like voice modulation, gesture, etc. There is what is called mutual intelligibility when two individuals which they don't share the same common language, and there is not a bridge between them, like for example a lingua franca such as English, that they can communicate by using their own language. An example that we can find is for the Scandinavian countries, for the Danish speakers, the Swedish speakers, and the Norwegian speakers, they can communicate between them by using their own language. They have this phenomenon. It has been widely studied by different authors, and it has been shown that this phenomenon is asymmetric. So for the case of the Danish speakers and the Swedish speakers, the Danish speakers can understand better Swedish speakers than the other way aside. And it happens also for Brazilian Portuguese in one study from Jensen, that they have found that Brazilian Portuguese speakers can understand better Spanish speakers than Spanish speakers. So we are interested in spoken intelligibility, and for studying this, we are going to focus on on the sound, and which conforms the sound for the speaking process. In this case, is the phonemes, that are these mental constructs, characteristics of every language, and they allow us to differentiate between words. They are these equivalence classes, and if two sounds they share the same equivalence classes, they are from the same phoneme, they are called allophones. For the case of dedo, finger in Spanish, if we change the first occlusive with the approximant, it doesn't change the meaning. But for the words set and cell, the last sound, it allows us to differentiate between the words. Okay, so we have defined all this, and we are computing the distance with the relative entropy. The relative entropy is just a measure that provides us about the inefficiency of describing one random variable with an approximating distribution when the real distribution is another. It has one of the most important properties for us is it's in general asymmetric. It doesn't hold equality. And the other thing is that if there is one element in the test distribution that doesn't be in the real distribution that doesn't belong to the test distribution, it will diverge. As we are working with phonemes and they are not always in all the languages, we will have divergences. So for avoiding this, we are introducing a smoothing parameter epsilon, and we are separating the contribution of the relative entropy for those elements that belong to both distributions and those that are only in the real distribution. Here are for the joint, and here for the exclusive phonemes or elements of the real distribution. So just a brief comment of what happens in this expression. We have the contribution of the exclusive elements of the real distribution in red, and the other ones are in blue. This is for the case of Portuguese and Spanish, one of the highest values of relative entropy in our set of values. And these are the phonemes that belong to the real distribution to Portuguese, and they are ordered in the according to the probability they have. So here we have the phoneme with highest probability, and here the one with lowest probability. What we see is that the contribution to the relative entropy from those elements that belong to the real distribution only, they contribute positively, and it's the main contribution to the value of the real entropy, the relative entropy. But for those elements that are that belong to both distributions, we can see that the contribution can be positive if the occurrence in the real distribution is higher than in the test distribution, and can contribute negative if it's in the other side. See, this is the same example, but for one of the lowest value of the set for Romanian and Portuguese. The important thing here is to see that the values that are exclusive to the real entropy, they contribute more. They are more important. Okay, well, this is what I just said, and we are using two other measures for our comparative study. One is the Jensen-Shannon divergence, that it's a symmetrized version of the relative entropy. And the other one is, it's bounded between 0 and 1. And the other one is the two-sample Kolmogorov-Smirnov test, that its null model states that both samples of data, they are drawn from the same continuous distribution. So that's it. Now let's start with the methodology. The methodology of this work is we are working with distribution of phonemes for each language. So we have to obtain these distributions. We obtain these distributions by taking some text for a language translated to that language. We count the number for each word. We count the frequency of that word, and then we transcribe that word. We make the phonetic transcription of that word. Then for each phoneme that appears in the phonetic transcription, we add the frequency that's related with that word. So then we obtain this distribution of phonemes and we normalize it. So we obtain a probability distribution function. I'm not a philology, I'm a linguist, so I don't know how to do a transcription by myself. So I've done the phonetic transcriptions by using this library from Python called Phonemizer, which allows to make the phonetic transcription of text in its orthographic form, and it's based on different backends. The one I've chosen is Speak because it made the phonetic transcription of about 100 languages, and it's based on the rules of the EPA, the International Phonetic Alphabet, that is the one that I'm using for the work. Okay, this Phonemizer package has been used for different studies, as they mentioned in the article. As I've said, I don't know if the transcriptions are well done. don't have the knowledge about this. So the first thing that we have done is to validate this library by comparing the transcriptions that we obtain with Phonemizer with two different data sets. The first one is Wikipedon, which is a software that extracts data from Wiktionary. The other one is 4in1, which is a multilingual lexical database. It's a study that contains this database with a total of 6,160 equivalent words in 4 different languages, English, Portuguese, German, and Spanish. And it provides also the phonetic transcription. So the validation is, well, the validation process is very simple. It's just to compare the transcriptions, one bit with the other. And if there is this match in any token of the transcriptions, we count it as an error of the transcriptions. And we do this in each pair of tools, of Wikipedon with 4in1, Wikipedon with Phonemizer, just to see that for Wikipedon and 4in1, that they are supposed to be validated, there are a lot of errors too. So the first thing that we see is there is a very low number of matches, below the 50%, not for every case, but in general. And what we have done is to eliminate the diacritics and the suprasegmentals from the transcriptions, and we have obtained an increase in the number of matches. So, well, we need to do a more in-depth analysis about this validation. And the first thing is that Wikipedon, well, our validation is reduced to the number of words that are equivalent between 4in1 and Wikipedon. The other thing is that Wikipedon, well, Wiktionary is a free source, so I think everybody can modify the things that are in there. So, and 4in1 in their article, they say that all the transcriptions have been validated by professionals. So now we are going to compare 4in1 with Phonemizer, and for doing this, what we have done is to study for all of these matches the Levenstein distance, which counts the number of operations for replacement operations, insertions, and deletion of tokens, to see if there is any systematic changes of this is arbitrary, all the errors that we find in our mismatches. So for example, for the case of American English, it's American English because they have also British English. Well, the number of coincidences of matches is very low, it's about 40%, but from all of these matches, what we see is that we require between 93% of the operations required, of the number of operations, with 1, 2 or 3 operations, we can obtain the transcription from 4in1, so we can obtain the match. And from this 93%, we can see that the replacements are the operations that are the main operations, followed by deletions, and finally insertions with a very low percentage of occurrence. So we're going to focus on replacements because if we want to see every deletion in the transcriptions, this will be a very hard work. But with the replacements, we can find the mapping and see, and we're allowed to see if this mapping is in some kind of it's justified or not. So the first thing that we see is all the changes that have a greater occurrence in the replacements above the 1% correspond to changes of consonant with consonant and vowel with vowel. This is a good starting point. So for the case of American English, we can see that there are systematic changes, and also that they are the probability of occurrence is greater for some of them and lower from the others. So the 37% of the occurrences are, for example, this change in for this lateral phoneme that has these allophones, which is generally dark for the case of American and Canadian English, and for Southern accents of the USA, the US can be clearer. Yes. And also, we find that a Phonemizer allows this rhoticity in the schwa phoneme that 4in1 doesn't contemplate, and also for the 7.2% of occurrence is from these two allophones. that appear in our changes. So we see that there are in some kind justified. What we also have done is to measure the Jensen-Shannon divergence, and we have obtained a value of 0.27, which is quite high, but we can also see that the Jensen-Shannon divergence is very sensitive to the presence or absence of some elements, as we can see that for the case of the lateral phoneme, there is this complete absence that we have seen before. And we also have carried out the two-sample Kolmogorov-Smirnov, and the p-value has been 0.99, so we cannot reject the null model. And we have done this for all the different languages, and we have obtained. The conclusion is that the changes are systematic due to allophonic variations, realizations of the same phoneme, or dialectical variations. In all the cases, we have not rejected the null model. And finally, the Jensen-Shannon divergence, the values are below 0.5, which is a high value, but there are some of them that is between 0.12 or something like this. But it's not all bad. And the final decision that we have taken is as the number of matches has increased with the absence of diacritics and suprasegmentals, we have deleted them. Now we know how to create the distributions. We have validated phonomizer. The last thing we have to do is which text do we use? We want that all the distributions are created by the same conditions. So we need the same text, and the text that we have used is the Bible, because these 4 reasons is the highest it's the most translated text. Yeah, all around the world. It has a systematic structure. It has a lot of words, and it's in the public domain. We have made an study of convergence of the average of the distribution function for 6,000 words, and we think that we can affirm that the distributions are stable. Okay, now let's start with the generalities of the 3 main Indo-European families. Well, phonemes are classified according to production in vowel phonemes or consonant phonemes, and those are classified also in according to the place of articulation or manner for the case of consonant, and the height, vagueness, and rounding for the case of vowel. But for keep it simple, what we are going to look is at the number of consonant phonemes and vowel phonemes. The first thing that we see is the number of consonant distinct consonant phonemes for the 3 families is the 2 times the number of vowel phonemes. For a more extensive word, what we see is which is the contribution of each of these types of phonemes, of the consonant phonemes and the vowel phonemes. Let's take a look for the case of Catalan. It has 30 consonant phonemes according to our distribution, and 11 vowel phonemes. But if we take the the frequencies of occurrence of each one of the different phonemes for the vowel phonemes in red and the consonant phonemes in green, and we assume their contribution, we obtain this value. So the total contribution to the probability for the case of the consonant phonemes is around 60%, but for vowel phonemes is around 40%. There is this difference of around 20%, but according to the difference between the number of phonemes, we can see that probably vowel phonemes, they have a higher occurrence. We do the same for all the language, and then we average all over the same family, and we obtain the average of number of consonant phonemes, the number of vowel phonemes for each of the languages, and the average on the contributions. We can see the same that for Catalan, the number of consonant phonemes is higher than vowel phonemes, and the contribution, the difference is not very big, the gap between all the contributions. So we can characterize the families by relating those 2 averages. For example, in the case of Slavic languages, it has the greatest number, the highest number of consonant phonemes and the lowest number of vowel phonemes. But the difference between the contributions is just 12%. So we can see that the occurrence is in general, highest for the vowel phonemes. For the case of the Germanic languages, we can see that they have the lowest number of consonant phonemes and the highest number of vowel phonemes. But the gap between the contribution is the highest. So they are more characterized by their consonant phonemes. And finally, for the Romans, they are in a certain of intermediate point. We can see this. This is what just I've explained by the 7 first phonemes with highest occurrence for the Romance family, the Slavic family, and the Germanic family. We can see that the density of points of the orange correspond to the vowel phonemes and the green to the consonant phonemes. They are in consonance with what I've just said. For example, Germanic languages, they have, for those with more occurrence, they have more probability. They tend to be consonant phonemes. But for Slavic, the first ones are vowel phonemes. So this is the characterization. And now we are going to compute the distance between languages with the relative entropy. For the case of the Romance family, when we calculate the relative entropy, we obtain this head map here where the rows correspond to the real distribution and the columns to the test distribution. So, for example, in this case, we have the case of Italian with Portuguese. It would be like, well, Portuguese is the real distribution, like it's the speaker, and Italian is the listener. We are trying to approximate Portuguese with the Italian distribution, and the value is 11.37. But if we calculate the same magnitude, but in the other way, when Portuguese is the test distribution, we obtain a value of 1.96. So Portuguese has more facilities to approximate Italian than in the other way. So we can see this clear asymmetry. If we plot the values of the relative entropy for each one of the languages, when it plays a role of the real distribution and when it plays a role of the test distributions, we can characterize the behavior of the different languages. As for the case of Portuguese and French, they are the one that approximate better the others, but are more difficult to approximate. For example, in the case of Portuguese, the values are above this straight line of equality. And when they are above, it means that the values, when they are approximated, are higher. We can see this in the head map. When they are the test distribution, the values tend to be lower, and in the other sense, they tend to be high, according to the colors of our head map. Well, Italian and Spanish, they play the contrary role. You can see that they are easy to approximate, but they have issues to approximate the others. And in an intermediate position, we have Catalan and Romanian. What we do next is we separate the contribution of the relative entropy in vowel phonemes and consonant phonemes, and we compute the absolute value of the relative entropy. We plot the percentage of the contribution for the case of the vowel phonemes versus the values of relative entropy. The colors are according to the head map. And for values that are below the 50%, that means that the contribution is greater for consonant phonemes. At values above, this means that the contribution is greater for vowel phonemes. We can see some kind of tendency that for lower values of relative entropy, the density of points is greater for consonant phonemes, and we can say greater density of points for high values for vowel phonemes. What we do next is we generate two distribution functions for just for the vowel phonemes and just for the consonant phonemes for each one of the languages. And we obtain these head maps that allow us to understand better what is happening inside the expression of the relative entropy. Just for the case of Spanish, we can see that the values in its vowel distribution, when it's approximated by the others, are very low. But when the distribution is a consonant of the consonant phonemes, its values are very high compared with the others. So with this, we can infer that the vowel alphabet of Spanish is considerably smaller than the other languages, and the phonemes that are in the vowel phonemes that are in the Spanish alphabet, they are also in the other distributions. And this is not the case for the consonant alphabet. It have these different phonemes with a greater occurrence of 1%, 0.9, etc. So the last thing that we do is to plot the values of the head map of the real distribution, with the values of the vowel phonemes and the consonant phonemes, and we plot them with the values of just the vowel distribution or the consonant distribution, and we obtain this linear tendency when we compute the Pearson coefficient, and this increase when we compute the Spearman coefficient with values about 0.9, and we see more dispersion for the case of the consonant distribution. So we can expect that the relative entropy is generally due to the vowel phonemes, but with some participant of the consonant phonemes for the case of the Romance family. We can do the same characterization for the case of the Slavic families. Here we can see the Polish is an outsider in this head map because it has problems to approximate other language, and it is not easy to approximate by the others. Slovak occupies a position similar to Spanish and Italian, and well, these behaviors that we have seen before. We can also make a description a bit considering the regional families, but this is just for characterizing the languages. And then we do the same procedure as before, and in this case we can see that there is there are more density of points for values around of the relative entropy. This is because we have 8 languages in the Slavic family, and in the Romance family we just have 6. But also we can see that the linear there is more dispersion in the consonant phonemes distribution than in the case before. So this is not just because there are more points, and here, the correlation, the linear correlation and the Spearman coefficient are higher than in the case before. So, as we have seen when we have characterized the Romance family in the previous chapter, we can see that the vowel phonemes they are the ones that determine the behavior of the relative entropy, and also the asymmetry that comes from the relative entropy. And then we make the same study for the case of the Germanic languages. Danish here appears as the case of Polish before. And well, Swedish and Norwegian as Ukrainian and Russian, that I haven't said that, but they are very close together. And the other cases, well, we can study them according to this. We make the same procedure as before, but in this case, what we found is the opposite behavior. We have a greater density of points in the contribution of consonant phonemes, below the 50%. If we make this linear regression, we can see that the coefficient for the Pearson coefficient and the Spearman coefficient are greater for the case of the consonant distribution, but they are also considerable for the case of the vowel distribution. So, as we have seen before, there is a greater importance of the consonant phonemes in the case of the Germanic families than with respect to the other 2 families. Well, these are the results, and at the beginning I've said that we have eliminated diacritics and suprasegmentals, but this adds some deviation to our study because there are phonemes, for example, in the case of French, that nasalization is a important effect in the vowel phonemes, but we are not considering it. So we are reproducing the same results that before, but by adding the diacritics and suprasegmentals, just to see if there is any correlation with what we have done. We can see that there is a more strong correlation with the vowel distribution for the case of Romance, and a lower correlation with the case of consonant phonemes. And the same happens for the Slavic family. So they are in synchrony with the other results. But for the case of Germanic, we have a greater correlation for the case of vowel phonemes, but the consonant distribution stays constant. So, well, these are all the results that we have found. And let's start with the conclusions. The first thing that I want to say is the objective of the study is to measure the distances between languages, but based on this idea of mutual intelligibility. There are experimental experiments about mutual intelligibility, spoken intelligibility between languages. We have tried to correlate our theoretical values that we have found, but mutual intelligibility it's a complicated phenomena that depends on a lot of things and not just the phonetic features of the languages. So I'm not going to mention what the correlation was. Well, we have calculated the distances between languages according to the relative entropy within the same family. We have generated probability distribution functions. We have validated the library that we have used. So I think we have validated the distribution functions and they can be used for other studies. The entropy values between languages have shown this asymmetry between languages, and they're us to characterize the families according to the importance, to the relative entropy, and to the asymmetry of the different types of phonemes, vowel phonemes and consonant phonemes. Then finally, there are future lines of research that one idea could be we have considered just discrete distributions. So we are comparing token to token, and that if there is a difference between the tokens, we are not considering them in the relative entropy. Well, the values of the relative entropy will be higher. So it will be interesting to consider continuous distribution for the phonemes as when someone is not a professional in hearing the sounds of the phonemes, maybe he cannot recognize that specific phoneme, and he can relate it with some other thing, but they form part from the same equivalence class, per se, in some way. Then we could do a clustering based on a asymmetric similarity matrix. There are the case of hierarchical clustering for asymmetric networks, just for seeing if we can recover the linguistic families by doing the clusterings, for example, or for looking down if there are other things that we have not expected. Other classifications, as for example, about the place of articulation, of manner articulation, and also analyzing the impact of vowel and consonant suppression from cognate words. That is a study that has been done, and I think it's interesting. And the bibliography, and that's it. 2 minutes passed from the video.
Thank you very much. Okay, thank you very much. So we now stopping the recording.